All right, here we have our last week 15 video with colligative properties. Colligative properties is basically the properties that depend on the solute. So if you change the solute, you change the properties. So sometimes it depends on what solute you add. If it's insoluble, then it may not have an effect at all. But if it is soluble, and we're assuming it is, then you can change the melting points and freezing points of the solution. So solutions, again, are homogeneous mixtures of solutes and solvents, solute being the little guy like salt or sugar, and the solvent being typically water. So one of the best examples or analogies, or at least applications to colligative properties, is your car. Your car's engine gets very hot, and if we don't have a way to cool it, it can get too hot and seize up, and that's very expensive to replace. So interestingly enough, if it gets too hot, we can add antifreeze, which keeps it from freezing. But uniquely enough, it also keeps it from boiling. It's just that saying anti-boil doesn't sound very cool like antifreeze. So when we add antifreeze to water, we make a solution that is pumped around our engine, cooled in our radiator, and then pumped again, over and over and over again as you go down the road. So the ability to put antifreeze into water gives you a solution that has new properties, now having a really high boiling point. If it can't boil easily, then it can stay cool enough to stay in liquid form and not vaporize, so that it can reach your radiator, get cooled even further before it's pumped back in past the thermostat to the engine itself. So the ability to raise the boiling point is the exact same thing as it is to drop the freezing point. The fancy terms for that is boiling point elevation. So we're raising it, we're elevating the boiling point, and then we're depressing or lowering the freezing point, in a sense, antifreeze. We can also change the vapor pressure by adding pressure to the liquid so that it can't vaporize as easily. So let's talk about each one of those briefly. It's all based on the boiling point. The boiling point and the freezing point are the temperatures at which we're affecting by changing the solute in the solvent. So you can imagine that water boils at 100 and water freezes at 0. And that's exactly what they're showing here. The energy required to heat water up is a Q problem. That's Q equals mass times specific heat times delta T. And that would be the same up here for water vapor. That would be the same down here for ice. You'd have to use a specific heat for vapor and ice separately in those kinds of calculations. For processes like these plateaus, those are other calculations. That's Q equals mass times the heat of fusion down here. It's Q times equals the mass of times delta H of vaporization up there. And those are other calculations like we saw already. So we're not going to repeat those in this chapter. But there are conversions or calculations that we could do based on things we see in the metric system chapter at the end. My point is on this exercise is we're changing the amount of heat needed to boil something or to freeze something. So we're basically making water boil more difficult and making water freeze more difficult. So as we raise the boiling point, that's called boiling point elevation. And as we drop the freezing point, that's going to be called freezing point depression. And by adding antifreeze to water, we can do just that. So even though we call it antifreeze, it's really anti-boil as well. We can also change the ability for water to vaporize by adding pressure to it. You can imagine when we see water boil in class, we have some beaker sitting on a hot plate. Crank it up to 300. We don't need to crank it to 300. We do just because we want to get out of lab early in many cases, but We crank it to 300 because it gets there fast. And the reason it gets there fast is because it's superheating the water at the bottom. The water molecules that are way down here only have attractive forces on top, so they're the first ones to bubble up to the surface. We also have water molecules up here at the very top. They're only glued on the bottom side, and they go first as well. So oftentimes we see steam, and then we see bubbles. Steam because that water at the very top surface is the easiest to vaporize, and bubbles because that surface that is superheated at the bottom, also easy to vaporize. So in a normal boiling point, what we see is the atmosphere pushing back. So as the atmosphere, the oxygen, the carbon dioxide, the nitrogen, everything else that's in that homogeneous mixture we call air pushes down, it's at 100 degrees when these water molecules that are surrounded on all sides, when they can push back. So then, how do you make water easier to boil? Well, if you want water to be easier to boil, you just get rid of the atmosphere. If you want water to boil slower, then you're going to add more atmosphere, more pressure. And that's exactly why we have a radiator cap on our cooling system of our vehicles, because when it builds up pressure, it's even more difficult to boil. So not only do we have the antifreeze helping us, preventing us from boiling by boiling point elevation, we're also using the vapor pressure of any antifreeze or water that does try to boil. It's going to build up pressure, and that's going to make it even more difficult for it to continue to build up more pressure and to boil at all, really. So you can see from this chart here, if you remove almost all the vapor pressure, 4.5 is almost, no pressure whatsoever, we can actually boil water at 0 degrees when it wants to freeze. We have machines called rotary evaporators that do just that, using the vacuum that we've seen in class for the aspirin experiment. So by heating the water, we can make it boil faster, but we can make it boil faster just by taking away the air that's pushing back on the water that's trying to be vaporized. So that's another colligative property. So the take-home message here is anything that we add to water will raise the boiling point, and it will drop the freezing point. You can't get one without the other. We can also affect boiling points and melting points, or condensing points or freezing points, either one. Same idea backwards. But we can change those by adding pressure above the liquid, making it more difficult for new gas molecules to form. Or we can take away all those molecules using a vacuum and make it a whole lot easier for gas molecules to form because there's nothing pushing back down on them. So a funny example of a lot of chapters really summarized into one is every winter we have a choice of what we put on the highways in order to keep them from freezing so that we can safely drive our cars down those highways below freezing. So do we put salt, sodium chloride on the roads, or do we put sugar? Which one's going to give us more bang for our buck, so to speak? One thing we learned about salt in our electrolyte chapter is even though we have 1 mole of sodium chloride, we really have 1 mole of sodium ions because they're going to separate in solution, and we also have 1 mole of chloride ions. So basically we have, for every 1 mole of sodium chloride formula unit, we have 2 moles of ions. So that means we're going to have 2 times the freezing point depression and boiling point elevation, which we're not worried about in the wintertime. So you might think that with sucrose, then it should be 2 times 12, 24, another 44, another 22. Wow, you get like 100 bangs for your $2 in this case. Problem is, that doesn't happen. When you put sugar into water, it can't separate into pieces like an ionic substance, sodium chloride, can. It's not an electrolyte. It can't break apart. It can't dissociate. So that really just means that 2 moles of sugar is equal to 2 moles of sugar. So in the end, 2 moles versus 2 moles, it's the same. So it's a trick question. But what's important about this idea of which one is actually better is moles. Since it's 2 moles to 2 moles, that's great. But if you're filling a dump truck full of sodium chloride versus sugar, what you'll notice is this will be 12 times 12.01 plus 22 times 1.01 plus 11 times 16. All of that equals 1 mole of sugar. And now we need 2 moles just to equal 1 mole of sodium chloride. So all of this times 2 is going to equal the same number of molecules in 1 mole of sodium chloride, which is just 23 plus 35.45. So you can see that you can get a lot more bang for your buck buying salt, because here you only have about 58 grams and change for 602 trillion ions times 2 in this case. Where with sugar, you're up in the 22s plus, 160s plus 144s. You're well, close to 300 and change for sucrose. So you definitely were going to want salt, because you can fill up lots of dump trucks and get lots of freezing point depression, because you get 2 bangs for every buck based on the atoms that separate from your mole. And per ton, there's a lot more 58 grams than there are 300 grams that have to be doubled just to get that same effect. So size matters. And in this case, sugar is huge. And it takes twice the amount of that huge sugar molecule to get the same effect as 1 salt formula unit that can be broken in half and provide twice that freezing point depression. Last thing we're going to mention before we close this chapter is soap. We've already seen it once, so we're not going to go into any great detail. But what we said earlier is not completely true when we said like dissolves like. It's true, but there is a hybrid molecule we call soap that can do both. So water is very good at dissolving polar substances because water is polar. Grease loves things like oil because they're also very similar and non-polar. So unless you're going to be using, dry cleaners that are bad for the ozone or some kind of, fancy organic molecules to deal with non-polars, we need a molecule that can be washed away with water, but also like the oil and the grease at the same time. So when we think about soap, we think about this molecule from a lipid where we have this water-loving hydrophilic head, and that's because it's ionic. It's part of that ester linkage from our lipid back in exam 3. We also have that fatty acid tail that's hydrophobic. It's a hydrocarbon. It's going to be nonpolar. It's going to like the grease. So it's going to have the best of both worlds. The problem, though, that we have with soap in general is it requires pressure in order to work. All those polar heads wrap themselves up into what looks like a little cell. All the nonpolar tails hang out together in the inside. So if you just throw some soap on your hands, it's not going to do any cleaning. You see doctors and surgeons in movies all the time. They scrub for 20, 30 minutes before a surgery, because I know that scrubbing is the only way to get the nonpolar tails to touch the bacteria, to touch the viruses that may have been on the door handles that they use on the way in to the operating room. So lucky for us, the lipid layer of the spiky coating of COVID is attracted to those little tails. All we have to do is rub our hands together with a little bit of pressure to get those soap cells to attract to them. And then our water that's coming out of the sink can wash them away. All using polarity and all using solutions in this case. So that finishes this chapter. We'll catch you next time for our last chapter with gases. See you then.